Let's get started. So the last class, we just introduced the topic of partial fraction expansion. And again, the reason why we have to do partial fraction expansion is we have a table of Laplace transforms from f of t into f of s. You can also use that table to go from f of s to f of t. So instead of doing the inverse Laplace transform or doing all those integrals that we sort of did a few at the beginning of the semester, beginning of this module, we're actually going to use partial fraction expansion. And the whole purpose for doing partial fraction expansion is addition in the time domain is exactly the same as addition in the Laplace domain. So as long as we can add individual functions, like this one is, we'll call this f1 of s, f2 of s, and on and on and on, we individually find out what each of those functions are, f1 and f2, then we just look at the Laplace table and we match it up and we're good to go. We can use the Laplace table and go back into the time domain. Most of the functions that we'll be analyzing, though, are not broken down neat and nice like this. You don't get a over s plus alpha 1 plus b over s plus alpha 2. You've got a bunch of numerator terms and denominator terms, and those are polynomials. And you've got to do a process to separate them. So we're going to do partial fraction expansion. And the whole thing about partial fraction expansion is we're trying to take the functions, right? Trying to figure out what the functions, and we would like them to kind of look like the table. So if you notice, the s plus alpha 1 looks kind of like e to the minus alpha 1 t, right? You look at your Laplace table, it looks just like that one. So we're not only doing partial fraction expansion to break them up into f of s, but we're also doing partial fraction expansion so that they're easy to just pull them up from the Laplace table. And so what we see here is by doing the roots here, and basically it's just taking the roots of your denominator and expanding it out in, all the way down to factored form, we can actually go ahead and easily do partial fraction expansion. All right, so this is the way that I suggest you do partial fraction expansion. And the reason why I think it's the easiest way to do it is because it's very consistent. We'll see there's a couple cases that this method has a little bit of challenges, but we'll come up with a different way. You can always go to that, partial fraction expansion where you have AS plus B and all those terms, and then, equate terms. But the problem is that you're actually going to end up slightly simpler results if you do it that way. So let's go ahead and do f of s equals 3s plus 7 over s squared plus 5s plus 6. And let's just bring up a Laplace table so we can toggle back and forth. And this is a pretty busy table, but if we look in this table, we're looking high and low. Actually, let's look at an easier table. That one's got a lot. Let's just do a simpler one. A more basic. How about this one? Let's see. No, it's got U's in it. We don't want U's. How about this one? All right. This one's pretty easy. Whoops. And I think these are mostly what we will need. So if we look at this table here, right, what we're doing is we're looking here. We are focused on, doesn't want to take the pen. We are focused on the transform. That is our expression or our function that is, in fact, in the Laplace domain. So what we're doing, again, is we're doing all our math in the Laplace domain, and we're trying to make it look like those elements in that transform column that we see there. So as a result, all we need to do is make it match whatever's in there. So if I go back, let's kill this and this. If we go back to here, is there anything that anywhere remotely looks like 3s plus 7 over s squared plus 5s plus 6? Let's go back. Well, the only time I see an s squared, right, is here. is item number 11 or number 12, and maybe perhaps item number 8, which is possible to have an S squared term, okay? But in each of those cases, it's got just one coefficient, like over here, zoom this one out here. In this one right here, you can see it's S plus alpha squared. So it's a completed square term. So we don't have that here. Why is this doing that? We don't have that here. It's not anywhere close. And then if we look at these other terms, we don't have a term that has an S multiplier in it as well. So you can see there's no way that those two expressions are going to work. So we can't use the Laplace table and bring this back to the time domain. That's the first thing you should check. Is there any Laplace table transform that the function already looks like? So you don't do partial fraction expansion if it already looks like the table. If it doesn't look like the table, you've got to do some partial fraction expansion. So let's go ahead and do that here. So we're going to go ahead and take those down into just getting the roots. How do you solve for the roots of a second order or less equation? First order is really easy. How do you find the roots of a second order equation? Do you all remember? Anybody? We did it on MATLAB, but what if you don't have that MATLAB or your calculator handy? Factor? You could do factoring. That's sometimes going to be tricky, right? It's sort of trial and guess a little bit. Is there anything else that maybe possibly you've seen? You all remember that? Algebra 2 days, right? Quadratic equation. That works for a second order system, right? That means it's S squared. So if you don't remember, AS squared plus BS plus C, to solve for the roots of this system, negative B plus or minus the square root of B squared minus 4AC all over 2A. Remember that, right? It might have been a minute, but it's something that's not super duper challenging. You just plug in the numbers. But I wanted to show this because these coefficients, it's really important to know where we get the A, B, and C from. So let's go ahead and grab that from here. So we have S squared plus 5S plus 6. S squared plus 5S plus 6. And this is supposed to match plus C, right? So clearly what we can see, A is equal to 1, B is equal to 5, and C is equal to 6, right? Just coming up with the terms. So now we can plug that into our quadratic equation. Negative 5 plus or minus the square root of 5 squared, which is 25, minus 4 times A, which is 1, times C, which is 6, minus 24, all over 2 times A. So that's going to be equal to negative 5 plus or minus, what's the square root of 1 equal to? Just 1, right? All over 2. And here's the thing. You see you have the plus and the minus there. And the reason why you have the plus and the minus is because you have 2 roots, right? If it's S squared, you have to have 2 roots. They can be equal to each other, but you got to have at least 2 roots. Or not at least 2 roots. You got to have exactly 2 roots. So that means I have root 1, which is equal to negative 5 plus 1 over 2. And root 2, negative 5 minus 1 over 2. So 1 is negative 2, and 1 is negative 3. All right? So to write that in, so these 2 are the roots, right? So to write that as the denominator, it becomes S minus root 1 times S minus root 2. Why did I put the minus R1 and minus R2 in there? Because the definition of a root is if I plug in that root, that term should evaluate to 0. So if I plug in R1 over here, doesn't R1 minus R1 equal 0? Okay, so this is very important. Make sure you have the negative of the roots there. Otherwise, they actually aren't the roots. Okay, you'll get bad numbers. So what we have is S minus a minus 2 minus a minus 3. Those are our two roots. Okay. So now let me grab the denominator here. So that's 3S plus 7. And at this point, if I could, if it's possible, I would love to use a table, but we've already determined we can't do that. So now what we're going to do, and I'm going to write this all out, in partial fraction expanded form, that's A over S plus 2 plus B over S plus 3. Okay? I have no idea what A and B are, but you get the idea. Now, here's what you would have probably done in the past. Tell me if I'm wrong. All I'm going to do is on the right-hand side, I'm going to put it back under the same S squared, S plus 2 times S plus 3. So 3S plus 7 over S plus 2 times S plus 3 is going to be equal to A times S plus 3 plus B times S plus 2 all over S plus 2 times S plus 3. Right? They should be the same. They should be equal to each other. So the denominators have to be the same. So now I'm going to throw out the denominators because they're both the same. So what I have is 3S plus 7 equals AS plus 3A plus BS plus 2B, right? Everybody following along so far? Right here? I just put it back under a common denominator. So you can see right here, I multiply by what's under here and multiply by what's under here. That's all I did. Just putting it back under a common denominator. So now I'm going to kind of equate terms. 3S plus 7 is going to be equal to S times A plus B plus 3A plus 2B, right? I know that whatever multiplies the S, it's got to be equal to 3. So 3 has to equal A plus B. And the terms that aren't all multiplying by S have to be equal to each other. Right? Got to be the same. So now I've got to do simultaneous equations, or I can use matrices, whatever you want. We'll just do simultaneous equations because it's pretty easy. So I can see that A is going to be equal to 3 minus B. So 7 is equal to 3 times 3 minus B plus 2B. 7 is equal to 9 minus 3B plus 2B. Let's see, negative 2 is equal to negative 1B. So B is equal to positive 2, right? And that means that A, and I can grab that over here or over here, it doesn't matter, A is equal to 1. Pausing a moment for station identification. Is this how you were taught how to do partial fraction expansion? Maybe. What's that? What part not? What part is missing? And it could be missing is like this was so long ago I can't remember.
Yeah, well, yeah, a little bit.
Okay. Sure. I'll zoom out. The order?
Something's off.
Something's wrong, is that what you're saying?
No, I don't think anything's wrong, just from the way I used to.
I don't know,
I understand what's going on.
but does everybody remember being taught partial fraction expansion? You could say no, that's perfectly fine.
The only thing I know is-
You did go over it?
Yeah.
Okay. So you may or may not have have been exposed to this, just depends if you can remember, right?
I think it might just be that I always did it in an integral.
Well, there is no integrals here.
I know, that's why I'm getting thrown on.
Oh, if you want, we could add an integral, but that makes it a lot more hard. I don't want to do that. Well, let's go ahead and check our results. Is it correct? Let's see. So I said 3s plus 7 equals s plus 2 times s plus 3, right? So that's going to be equal to 1 over s plus 2 plus 2 over s plus 3. If we calculated our coefficients correctly, right? So let's check and see. S plus 3 multiplied by 1, putting it back under a common denominator, plus 2 times s plus 2, all over s plus 2 times s plus 3. S plus 3 plus 2s plus 4, all over s plus 2 times s plus 3 equals 3s plus 7 over s plus 2 over s plus 3. Is that the same as that? Phew. Means we did our work correct, right? Means we got it right. So this is one method that you're welcome to use to do it. But look how much work it was, right? We basically did all of this part here, right? To get the answer. I'm going to show you, I think, an easier, more efficient way. The first time you do it, it doesn't look easier or more efficient. But if you practice it, then it becomes really easy and efficient. So let's go back to here. We'll start at pretty much the same spot, right? Everybody okay with that? That's starting at the same point. Let's say I want to solve for A first, and I don't want to do this method. So let me think, I'm going to try a trick and see if this works. I'm going to multiply both sides, right? Because it's S algebra. So as long as I multiply both sides by the same thing, I haven't screwed anything up, right? I get the same result. So let me multiply both sides of this expression by whatever is under the A term. Okay? So 3s plus 7 all over s plus 2 times s plus 3. And I'm going to multiply that by what is under the A term. So I better do that on the other side. Okay? Did I break any any algebra laws? Looking like I'm okay. So now I'm going to go ahead and cancel some stuff out. I'm going to cancel the s plus 2, right? They cancel out. And I'm going to cancel that s plus 2. That's all I can cancel out. So what I've got is 3s plus 7 over s plus 3 is equal to a plus b times s plus 2 over s plus 3, right? Darn it. I really was hoping to make my life easy and be able to solve for A using this method. But I still have A and B there, and I don't know what B is, right? So I only have one equation, but two unknowns. So did I help myself out, or did I not really do anything? Well, what do we know about a linear equation? If I can find unknown coefficients, for any value of S, those coefficients will work for any single value of S. Doesn't matter if it's 50, 5 million, 500,000, it works for all coefficients. So is there perhaps a way that I can plug in a number for S and maybe be able to solve for A?
Yeah. Make S -2.
Yeah, if I evaluate this expression at S equals -2, and that means both sides, right? What happens? If I plug in -2 right here, -2 plus 2 becomes, and B times 0 becomes, so A equals 3S plus 7 over S plus 3 when S equals -2. So that's going to be equal to 3 times -2 plus 7 over -2 plus 3, which is equal to -6 plus 7 over 1, which is equal to 1 over 1, which is equal to 1.
But that only works if you're getting one of the coefficients equal to 0, right?
Multiplying one of the coefficients by 0.
Okay.
It doesn't equal 0, it multiplies by 0. But yes, that's correct. Got it? Because let's check our work. Over here, we said it was 1. Didn't we also say it was 1 right there? When we did the other, just basic algebra approach, not doing more of this fancy algebra. So that looks like it's pretty good. Now let's double check B. So to solve for B, I'm going to multiply both sides by whatever is under the B coefficient. In this case, S plus 3. And I got to multiply both sides. Right? Cancel out what I can. And what I'm left with is 3S plus 7 over S plus 2. Y'all have any suggestions of what I should maybe plug in for a value of S so that my A term goes away? -3. So if I evaluate at S equals -3, what I'm left with is 3S plus 7 over S plus 2, evaluated at S equals -3, equals A over S plus 2, times -3 over 3, or -3 plus 3 plus B. This term goes to 0. So what I have is 3S plus 7 over S plus 2, evaluated at S equals -3, is going to be equal to B. Let's plug it in. 3 times -3 is -9, plus 7 over -3 plus 2 is equal to -2 over -1, which is equal to 2. Is that what we got from before? Sure is. So you can do two ways. You can either do this method. We'll call this method, we'll call it old. Can't tell what I'm trying to do, right? And we'll call this method new. Now, again, do you remember what I said? How's this saving me any work, Paul? This looks like a lot of math. But here's the thing. Once you get good at it, this is what you can do. We'll start off at the same spot. 3S plus 7 over S plus 2 times S plus 3 equals A over S plus 2 plus B over S plus 3. If I'm really good at solving this, here's what I do. A equals 3S plus 7 over S plus 2, s plus 3, sorry, evaluated at s equals minus 2. Isn't that basically what we get to? Really quick, right? I got this really quickly. And we already know that that's equal to 1. And then B, I could certainly solve for B by plugging in my A in here, right? Because then I only have one equation, one unknown. But why would I bother? Why wouldn't I just do that? Isn't that faster? And it's the same process, the same technique over and over and over again. So this new method is what I suggest you do. Pausing to make sure you understand how to do this. Kind of sort of getting it? Need a little more practice? Okay. That's all the stuff that we specified here. Now, once we have the the partial fraction expansion, then it's a piece of cake. We go to our Laplace table and we can see that 3s is going to be equal to 1 over s plus 2 plus 2 over s plus 3. If I look at my Laplace table, we can see right here, item number 6, that 1 over s plus alpha equals e to the minus alpha t. So over here, alpha equals 2, and over here, alpha equals 3, right? Those are what the form is. So now, if I look closely, you'll notice in item number 6, there's a 1 for the multiplier up top. I'm good to go for this one. What about right here? I've got a 2. So how do I deal with that? No problem. This is 1 over s plus 2 plus 2 multiplied by 1 over s plus 3, right? Multiplication by a constant in the time domain is exactly the same as multiplying by that same constant in the Laplace domain. So I can take this function back here and get f1 of t, and this one over here and get f2 of t, and then I just multiply by that same constant. So this becomes e to the minus 2t plus 2, because there's my constant, right, that I multiplied the f of s by. That becomes e to the minus 3t. That is equal to my time domain solution, or my time domain result.
You say you multiply the constant?
Yeah, so this constant right here, number 2, the number 2, is multiplying a Laplace domain function, right? 1 over s plus 3 is being multiplied by 2. 2 is a constant. So I multiply my f of t, I've converted it back into the Laplace, in the time domain, and I multiply it by that exact same constant. Henry brings up a good question. When we did our last one, what did we say? What can't you multiply by? I can't multiply 2 functions in the Laplace domain and get the same 2 functions multiplying the Laplace domain. Those are functions. Those have s terms in them. You see any s terms in here? It's just a constant. And you can check it because remember, f of t, the Laplace transform of that, is equal to the integral from 0 to infinity, f of t, e to the minus st dt, right? That's the definition. I can take the Laplace transform of 2 times f of t. That's going to be equal to the integral 2 f of t, e to the minus st dt. When I integrate that expression, is two in a variable of time? Absolutely not. So that becomes two integral. Well, isn't that the definition of f of s? So that's just two times f of s. So as long as I multiply by a constant, no problem. But if I multiply by a value that has an s in it, I can't do that. Okay? That's how we ended up with that expression. And it's pretty simple. Two decaying exponentials. Make sense? Don't make sense? Need practice? Good. Your turn. Remember the process that we did for partial fraction expansion. I'll give you a hint. The very first thing you should do, you're not sure, start off with the quadratic equation and see if you can get something that looks like the table. That's the very first thing you should be doing. Quadratic equation, go from there. You can do whatever you want. You can do the the A plus B terms and do it that way. Or you can do it the way that I've been suggesting. Quadratic equation. I'll write that here. So negative b plus or minus the square root of b squared minus 4ac all over 2a. Arthur said, I think you have to do this in Calc 2. Right? But I wouldn't imagine why you need that in Calc 2. I'm not saying I disagree with him, but I don't know why they would do it in Calc 2, because it's just an algebra thing, right?
There were certain integrals that you had to do PFE in order to break it down in order to get individual integrals to integrate.
Ah, okay. So you break them up
Yeah.
and then it's easier to integrate them. Yeah.
Multiple.
Yep. Same thing here too, right? It's the same thing to break them up into separate terms and then bring them back into the time domain.
Correct me if I'm wrong here, but we're going to get a negative radical.
Let's see. We'll see. I don't think you're going to get a negative radical, but I could be wrong.
Well, 16 minus 4 times 29, I think is
Okay.
looking at there, right?
Give people a couple more minutes to see what to do. All right, let's try it. Quadratic equation, like everybody said. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Anybody else get that?
Yep.
Now, I argued with Arthur and I said, I'm not going to have a negative radical sign. Why not? Because we're electrical engineers.
Well,
And
yeah,
we
you get a,
love to use complex numbers, right? I don't see any negative radical there, do I?
no, but it's a complex root.
It's a complex root. So I'm being a little bit silly because clearly Arthur was right. You would have the negative radical, but it's easier for us to deal with. We just put in the J term, doesn't it? That's not not a negative term anymore. I mean, it sort of is, but we just factored out the J. No big deal, right? All over 2, -4 plus or minus J10 over 2, which is -2 plus or minus J5 or 5J. So one of the things you will not see in this class, you will not see any negative radicals because we'll just substitute J. Okay. So now let's look at that. So we have 2 roots. We have S1, -1 plus J5, and S2 equals -2 minus J5, right? There are 2 roots there. So if I wanted to write those, I would go S minus a -2 plus J5 times S minus a minus, oops, too many minuses outside the line here. -2 minus J5. Right? That's a mess because we know what we just said. Alpha is going to be equal to a -2 plus J5. That's alpha 1. And alpha 2 is equal to -2 minus J5, right? If we looked at our table. And in the Laplace domain, we're going to get this. You see many expressions in the real world that have e to the j something in them? I don't. So here's what happens when you have complex roots. Here's a suggestion. Okay, you can do this, but there's a lot of work to do it. Instead of going over here, whenever I have a real part and an imaginary part, I'm going to call that term alpha, and that term is going to be omega. The alpha is associated with a real part, the omega is associated with a complex part. And instead of going here, I'm going to do S minus alpha, that quantity squared, plus omega squared. So let's plug that in. S minus a -2, that quantity squared, plus 5 squared. That's a good thing, right? No complex numbers. They're all real. S plus 2, quantity squared, plus 5 squared, right? That's what that works out to be. If our work is correct, we should end up with this initial expression right here, right? Should be S squared plus 4S plus 29, at least in the denominator. So let's see. This is, I'm going to FOIL that term. So I have S squared plus 2S plus 2S plus 4 plus 25, which is equal to, collect all the higher coefficients, S squared, that becomes 4S, and that becomes 29. Does that match our original number? Sure does. So doing this approach here is highly encouraged, highly suggested, because you don't want to have complex numbers when you're in the time domain, because you can't make a waveform that looks like that. But if I go back over here and I take my 5s plus 40 and I put it in s plus 2 squared plus 5 squared, that's my f of s. Now I'm going to go look at my Laplace table and see if there's anything that is remotely like this. So do I have any functions that have an s plus alpha squared plus omega squared? Let's see. Oh boy. I see s plus alpha squared plus omega squared in two spots. Item 13 and item 14, right? And you'll notice item 13 has an s plus alpha in the numerator. So if I go back over here, I know that alpha is equal to 2. So what I'm going to do over here is I'm going to say s plus 2 over s plus 2 squared plus 5 squared. Looks just like one of these items in the table. But I also have some leftover stuff here too, right? So let's take that out. And this is s plus 2 squared plus 5 squared. Well, what's the leftover stuff that I have? I've got to be careful because I only have an s coefficient over here in this cosine waveform, right? Item number 13. So what I'm going to do is I'm going to go back over here and I'm going to factor out 5 out of that expression. So what I have, let me give myself a little bit more room here. I'm going to put the 5 all the way out at the beginning, right? So I can see all I'm trying to do is replace the s plus 8. So I've got s plus 2 over there, and I've got 6 left over.
How do you get the 5s plus 8?
5s plus 40. If I factor out the 5, what do I get? 5 times s plus 8, right? So I'm grabbing s plus 2 over here to make that first one, and I'm missing 6 over here. So that's just basically the remainder to make that work. And now I'm really darn close to the table, aren't I? Because this one right here is item number 13 on the table. Looks just like it, except for it's multiplied by 5, correct? But the other one has to be tweaked a little bit because it's not alpha in the numerator, it's omega. And what we know is omega is equal to 5, right? So what we have to do is another modification. Here's s plus 2 over s plus 2 squared plus 5 squared plus I need to have a 5 over here, right? But I had 6 over here. So what do I do with it? Factor it out. I factor out a 6, but I darn well better divide by 5, right? So I end up with the term, the 6 there.
Can you break that part? What everything is saying?
Yep. So I have a 6 right here, right? That's a 6. But it needs to be 5 because if I go back to this Laplace table, I see in item 14, I get omega in the numerator, right? Not some random number. It has to be omega. Over here, I know that omega is equal to 5. So when I write my equation, I just put a 5 in the numerator because that's what it has to be. So what I've done is I've multiplied by the original coefficient, which is 6, and then I just divided it by 5 to cancel out the 5 that I have here. So basically all I did was I moved the 6 out front I put a 5 over here, and because I multiplied by 5, I darn well better divide by 5. Make sense? So now I have 5 times s plus 2 over s plus 2 squared plus 5 squared plus 6 times 5 over s plus 2 squared plus 5 squared. Notice I multiplied both of those individual f of s terms by 5. That's why it canceled out over onto the 6. And so my final expression in the time domain, my f of t is equal to 5 e to the minus 2t cosine of cosine, not co5, cosine of 5t plus 6 e to the minus 2t sine of 5t. I didn't even need to do partial fraction expansion on this one, did I? Because the denominator, right, of these expressions looked like the Laplace table. So I didn't do any partial fraction expansion. I just did a little bit of math. Pausing now because this is a lot, right? A lot of math.
Paul?
Yes.
Should it be 6/5 or just 6?
It's 6 because if you look over here, remember when I factored out the 5? I factored it out of both expressions. So I had to multiply, which means I canceled out the 5 that was in the denominator.
Okay, cool.
Okay. So this one I just made it look like the table. No partial fraction expansion. Want to do another practice one? Or do you want to go home and go to bed? Could be both ways. This stuff isn't easy. I will freely admit that's why we're really going like in exhaustive detail. But I'll help everybody out. I will. This wakes up. I'll give you a homework problem. Freebie. Because the homework problem, it's only 3 parts, but you will notice 1 and 2 have a lot of parts to them, so hopefully a minute.
Well,
Only 3 questions.
But let us do E. Okay, does that seem reasonable? E on problem 2. We're going to go back from the Laplace domain to the time domain. So you want to try it yourself or you want me to go through it? Your choice. All right, I'll give you 5 minutes. Try away. Remember step 1, solve for the roots. Use the quadratic equation. It is your friend. One more minute.
Okay. Yeah, well, I agree. I don't mind.
All right. Everybody feeling good in the middle? All right. Well, for those of you who are feeling confident, you can keep working. I'll go ahead and I'll do it. And then we can compare answers because I'm not infallible. I make mistakes. So negative b plus or minus the square root of b squared minus 4ac all over 2a. So we have -3 plus 1 and -3 minus 1, which is going to be equal to -2 and -4. So my f of s becomes 5s plus 16 all over s plus 2 times s plus 4. Remember, we have to put in the negative there. No, yes, maybe. Okay, so let's look. Our step. Is there anything that looks anywhere remotely close to being on the table? I don't see anything. The only way you could make it work is if somehow, like this s plus 16, if you could cancel that out here in the denominator, you know what I mean? And kind of make it sort of work, but I don't see any way of really being able to make that work because you'd have to divide by 4. So you'd end up with a mess. So,
PFE.
pardon?
PFE.
PFE, yes, very good. A over s plus 2 plus b over s plus 4. Now, do you want me to write it the long way to solve for a and b, or do you want me to do it the efficient way?
I like the efficient way.
Yeah, I did the elimination method too.
Okay. So a is going to be equal to 5s plus 16 all over s plus 4, evaluated at s equals -2. I didn't show the multiplication by both sides by s plus 2, and then the canceling it out. I went right to the final approach. And that becomes 5 times -2 plus 16 all over -2 plus 4, -10 plus 16 all over 2, which is going to be equal to 3, correct? Anybody get 3 for A?
Well, I just got them swapped, I think.
Okay, that's fine. Let's check out for B then. 5s plus 16 all over s plus 2, evaluated at s equals -4. So 5 times -4 plus 16 all over -4 plus 2, -20 plus 16 all over -2, which is equal to 2. So my final f of s before I'm ready to take it into the time domain is 3 over s plus 2 plus 2 over s plus 4. Anybody else get those? Couple people?
I got it.
You got it?
Got it. putting my feet.
Ah, it happens.
I just had the A and B swapped, but it came out the same.
Oh, that's okay, yeah. It doesn't matter. You can do A and B first. You just make sure you put them under the right coefficients.
Well, it just has because I grouped it S+4 times S+2, where you had it grouped S+2 times S+4. So when I split it up,
Yep,
they were just swapped.
yep, no, that's fine. But what I'm saying is as long as the 3 is over the S+2 and the 2 is over the S+4, that's the important part. As long as you got that, that's all I care about. So that's 3 e to the minus 2t plus 2 e to the minus 4t, taking back to the time.
Can you go back to when you did the quadratic equation?
For this problem? Yep.
Like how you decided that you couldn't do it that way and had to do it the partial fraction?
How I couldn't do it the quadratic equation? Because I did the quadratic equation no matter what. No, I used the quadratic equation to give me the roots, which gave me these two parts right here. Right? I did the quadratic equation to know what the roots are so I could factor out the denominator. So I did that no matter what. In either case, whether I do partial fraction or not, I've got to figure out what the roots are. Since this is a second order system, I can use the quadratic equation.
Because you also get plus two, and then S+4 can factor in
That's what I
the
do.
original.
When it's easy, when the numbers are easy like that, yeah, but like the last one, the numbers weren't so easy. You have the quadratic.
So yes, so I didn't understand your question, I guess. You can go ahead and factor it. Because like Drew said, it's easy. But I don't even care if it's easy or not. I just use a quadratic equation and it can be easy, it could be hard. Doesn't matter to me. I just use a quadratic equation and it spits it right out and it spits out the correct result. So you can certainly factor, you just got to be careful that you don't make mistakes. That's the nice thing
Well,
about the
that's
quadratic
right.
equation.
I just looked at that and in my head, like I could figure out what it would be, but I had everything swapped. I had S minus to S minus to it.
Ah, so you ended up with the same roots that I did, but you didn't plug them in here into the correct
Right.
format, right? Because it's S+2 and S+4.
Yeah.
But yes, you can factor. If you went to MATLAB, and I don't suggest you do a lot of this because you can set yourself up. It was 1, 6, and 8. Is that correct? Or no, 1, 8, 6.
That's funny. I just put it in a MATLAB myself.
Yeah. And you get -4 and -2, exactly what we calculated using quadratic equation. So if you want to do that, that's perfectly fine. I just like doing the quadratic equation because you're never going to have more than a second order circuit in our control systems class. You'll
Oh,
have second order circuits and a bunch of first order circuits or a bunch of second order circuits in your final answer. Go ahead, Arthur. Sorry.
I was gonna say I think that's interesting that MATLAB didn't scream at me for I delineated the roots with commas and it didn't scream at me. It actually gave me answers.
Yeah, commas or spaces work the same in MATLAB. So either way works fine. Sure. Here's the table. Right here.
So, yeah, that, you took that, put it, or the table. That's how you got it.
Yeah, because if I write that out, that becomes 1 over S+2 plus 2 over S+4, right? And if I look at the table and if I look at item 6, item 6 is 1 over S plus alpha is equal to e to the minus alpha t. So I literally just said, well, that's exactly the same, just alpha is equal to 2 or alpha is equal to 4. Piece of cake. One is before time t equals 0 and one is after time t equals 0. And since we're using unilateral, we're always going to start at time t equals 0. Okay. Is that helpful? Not helpful? The practice? You'll have some chances to do other ones. I mean, and getting good at partial fraction expansion and doing it very efficiently is really important to do well in this class. Because once we have a really good handle on the tool, we're actually going to start solving actual equations or actually solving circuits using partial fraction expansion. And then next semester, because it's a lot of work to do partial fraction expansion, next semester we won't even do going back into the time domain. We'll just leave everything in the Laplace domain. That's kind of what we're working towards. What if you have, like in the example I asked you to try, and you could just make it look like the table? What if you can't? What if you have complex roots? Clearly, I can see I've got complex roots in that term. This one, right, is easy. This is just s plus 4, right, when you factor out the 2. So I plug in -4, and I'm good to go. If you have an f of s that you can't break down into matching the table, if I've got two functions, so this is going to be s squared plus 4, and this is going to be s plus 4. If I've got two functions that I have to do partial fraction expansion, I can go back to, remember how when we did the, how we did the e to the minus j theta way up here someplace? Yeah, over here. We had e to the -2 minus j5, e to the -2 plus j5. But we're like, those aren't real world expressions. But if you recall from maybe 2 classes ago, we proved how the sine and cosine were going to be equal to some e to the j somethings, right? Well, we're going to take advantage of that as well. And instead of breaking this down all the way to s, because we could break this down to 1 over s plus 2j plus 1 over s minus 2j plus 1 over s plus 4, right? Actually, not say 1. Let's make those coefficients. We could certainly do that, but then we're going to end up with e to the -2jt in the time domain. We don't want that. That expression doesn't exist. But we know that we can combine the e to the -2j and e to the plus 2j to either get a sine or a cosine. So what we're going to do is we're going to make this number a complex number. We're going to call it b at an angle of theta. Not b, but b at an angle of theta. So anytime you have complex roots that you need to do partial fraction expansion, you're going to go b at an angle of theta. So that is b at an angle of theta. And then we'll make that a. How do you think we solve for a? Or c, doesn't matter. A is a piece of cake, right? It's 20 s squared plus 4, evaluated at s equals -4. So that's equal to -80 over 16 plus 4, which is -20, right? To solve for b at an angle of theta is very similar, except we have two roots. We're going to solve for it using, I said 20 over s, not, it should be 10 over s, sorry. So that should be, not, that should be 40. That should be 10. So b at an angle of theta is 10 over s, all over s plus 4. We're going to evaluate it at a root, but it's going to be the positive complex root. So that's going to be equal to, oh, it doesn't want to write on there. That should be a plus, and I don't, there we go. S equals -2 plus J4. So that's going to be equal to 10 times -2 plus J4, all over -2 plus J4 plus 4. So that's equal to -20 plus J40, all over 2 plus J4. no S terms. But I can see that I've got a complex number divided by a complex number, which most likely means I'm going to have a magnitude and an angle for my B at an angle of theta. So what I end up doing is, no, wait a minute. What did I call that? Oh, I screwed this up. Sorry about that. It's not -2. I'm a little slow today. Sorry. It is evaluating at S equals positive 2J, not -2 because there's no real part. So that's equal to 10 times 2J all over 2J plus 4. That works out to be 4.47. How do you check that? Let's go over here. Let's go to MATLAB. So the number is 10 times 2J over 4 plus 2J. So 10 times 2 times J divided by 4 plus 2 times J. Where did I end up with 4.47? That's not right.
Yeah, I was gonna say that seems kind of sus.
So let me look at the absolute value. Let's do that again.
Oh, right, yeah,
They-
you will have a magnitude, but you should have an angle then.
Yes, so that's the 4.47. I forgot to write the angle, or so it's 4.47 at an angle of 63. Why did that? I have it here. I wonder if MATLAB, the PowerPoint just burped at having the angle button. So let me modify that equation. I'll show you all my tricks. There is an angle symbol here. Where is the angle symbol? Try geometry. At an angle of, what did we say it was, 63,
Yeah, 63.63, I think,
43.
43.
And you've got to evaluate at the positive complex root, and it has to do with like sines and cosines. If anybody wants to find out, what the details of why that actually does that, there's a pretty specific reason, but we'll just always evaluate at the positive complex root. So now we end up with our Laplace, right? So we know that this is B at an angle of theta. This is my A term. So we're going to take the inverse Laplace transform. So we have 4.47 at an angle of 63.43. S squared plus 2 squared minus, is it 2 or is it, did I get that incorrect? It's 40 divided, yeah, so this is -2, right? So 40 divided by 20 is -2, not -10. So that's -2. So this is -2 over S plus 4. This one over here looks really close to the table already. The other one isn't. Let's go back and look at our table. And our table says, if I look at item number 12, I have omega over S squared plus omega squared. So all I need to do is put a 2 over here. I've multiplied that by 2. Now I have to divide that by 2 as well. So going back into the time domain, my f of t, and I'll do this one first, that's equal to -2 e to the minus 4t plus, this is 4.47 over 2, which is the magnitude, times the sine of omega t, which is 2t, plus the phase shift that we calculate. So it's the sine of 2t plus 63.43 degrees. And notice I specified the degree here. And the reason why is because this is in radians per second, right? The omega is in radians per second, and that is 63 degrees. So if you try to calculate what your results are, you're going to get really wonky results because you're mixing your units. But that is the final expression. When you have a complex root. All right. I think we're just about out of time. But the last thing, right? So we did partial fraction expansion, our modified approach is you simplify it. So if you have all real terms, you just do A plus B plus C, and then you just solve for it by multiplying by whatever is under the root you're trying to solve for and evaluating at that root. If you have complex, you solve for B at an angle of theta, evaluating it for the complex roots. The next one we'll pick up is if you have repeating roots, and we'll see why we need to do a slightly different modification for repeating roots. Other than that, there's no other challenges to this approach that we're using, which is always evaluating under the root, evaluating whatever the coefficient we're trying to solve for, and evaluating at one of the roots. All right, I'm out of time. Have a great weekend. I know you get lab tomorrow. But that's it. Any questions?
No,
All right, y'all.
I can think of. Thank you, though.
All right, have a great day, everyone. See
Thanks,
ya.
Paul.
I'll be on campus tomorrow if you need me, so see you then.
Thank you, Paul.
Thank you.